So for the analog and digital section, I decided to use a single turn 10K pot in voltage divider configuration to feed into an A to D channel, and this will allow me to exercise that over its full range. So that's the part number that I'm using if you're interested, and of course it's just a little three-legged guy that would be suitable for putting into a breadboard or through hole on a PCB design. So it's a nice little device. As far as the digital output goes, I'm going to use a standard 5mm LED with a current limiting resistor. Once again, this will be just a 330 ohm resistor. And I'm going to use an APS11700 series Hall effect switch on an analog port, actually, to measure if a magnet is nearby and then turn the LED on or off as a result. So this is one of the things we can do. Even though this is going to behave like a digital device, we can still use an A to D port pin. So we'll get to see that. We just have to set up an appropriate threshold for it. And because the Hall effect switch is an open collector device, we will need a 10K resistor to pull the pin up. And when the Hall effect switch is active, it'll pull the output low. So those are the three devices that I'm going to add to the board, and those are their part numbers. So here is the circuit that has been updated. I've excluded the power section because it hasn't changed, but I've added a Hall effect sensor. So this is a nice 3-pin device that provides an output that's either on or off, but it's open collector, so we need to use a 10K resistor to pull it high so that when the switch is off, it floats high. And I've connected that to PC2. I've added a 1-turn 10K pot, and I've used it as a voltage divider and fed that into analog pin. And I've added an green LED, standard LED, on one of the GPIO pins so I can use it as a digital output. So here's the circuit updated with the sensors. There's the Hall effect sensor with its pull-up 10K resistor, so I can get in there with a magnet to test it to see if it's working. There's my indicator LED with its current limiting 330 ohm resistor, now on a digital pin. And buried over here where I barely had room to put it in is my 10K pot, and it is set up as a voltage divider with its center tap going to a analog pin. And I've actually got the Hall effect sensor on an analog pin as well. So there's my circuit modifications with the Hall effect, LED, and potentiometer. So in a previous video I discussed how to move a sketch into Microchip Studio. So I'm not going to go over that again, but the good thing about this Arduino sketch is it has a whole bunch of examples that show you how to do some of these more basic things. So under the examples, there's a blink example, for example, which will show you how to do things like configure pin modes for digital input and output, and how we can actually write on or off values basically to those pins, as well as the delay function, which is kind of useful. There's also examples in here on how to do basic serial stuff and analog stuff, and in fact there's one that does both. So this analog read serial example shows you how to bring up the serial port, how to read an analog pin. So this is 10-bit A to D, so these values will come back as 0 through 1023. So we can read these voltages from the world and then make decisions on them. In this case, we could fire it out over the serial port at 9600 baud to a terminal. We can see those values as we're reading them. So these are really, really good places to start. You could really use any one of these to feed into your Microchip Studio code or your project. And we don't need to go through that process over and over again. Once you've created one, you sort of have all the stuff you need to use the Arduino libraries. So you could excise pieces out of other examples and just bring them into your already made project and add to it as you go. So I've taken some of those bits and pieces from various things and included them in this sample. So a few things to point out here. I'm using this chip right out of the package, which means it's relying on its internal RC oscillator. So it's running at 8 megahertz divided by 8 in its default setting, so the chip is really only running at 1 megahertz, which is really conservative, but it means it can run without any external crystal. So This is fine, but the libraries for Arduino expect the device to be running at 16 megahertz. So when we start doing things like initializing the serial port at 9600 baud, it's expecting to be doing that at 16 megahertz. So really it's being divided by 16. So if I do this initialization on the terminal side, the baud rate really will be 600. So I'll do that when I go and connect this to the Analog Discovery 2 and try to look at the serial output, because it's not going to be running at 9600 baud. So in the next video, I think I'll discuss this and provide the instruction on how to add the crystal to the circuit and how to set up the fuses in the device to permit 16 megahertz operation. So that'll be the next thing we look at, and then we don't need to worry about compensating for this device running significantly slower than the libraries expect it to. Okay, I've configured the pin that's connected to my LED, so this is an Arduino pin number, digital pin 8 to my green LED as an indicator, so that's done in the one-time inits. And then in my loop, I read the pot value, so my potentiometer is hooked up to analog pin 0. So I read the value. Again, this is a 10-bit value, so it's going to be anywhere from 0 to 1023 when I read that in, and then I just shoot it out over the serial port so we can see it. So if I hook up a terminal monitor to this, essentially, I can look at the TX pin of the chip and see what serial information it's firing out of the UART. So these functions provide the behavior of even taking numbers and formatting them into text, which is really nice. So you don't have to do stuff like that. Okay, and beyond that, I have my Hall effect sensor hooked up on analog pin 2. So I'm reading that value, and effectively it should be a digital operation coming out of that, but I can still hook it up to an analog pin and read the value. So I'd be expecting it to be 0 or 1 when the Hall effect sensor is on, and I would expect it to be pulled high by that 10K resistor when it's off, so it should be at 1023. But instead of checking specifically for those values, we could use threshold values to make sure that if it's anything below 100, it's on, and anything above 100, it's off. So I can use that to turn on or turn off my green LED on digital pin 8. And as far as my delay goes, again, the library expects this is in milliseconds, but it's in milliseconds if the clock is running at 16 megahertz. So I'll just divide that by 64 to provide quarter-second intervals. So the updates come a little bit faster. But I certainly can't use this expressed as milliseconds because I'm running at 1/16 the rate it expects. So now that I've got the pot hooked up as a voltage divider on that analog pin, I've decided to blast the value out in the code to the serial port. So I've got the serial pin hooked up to my Analog Discovery 2. So digital input pin, or digital I/O pin 1, is connected to the TX pin of the 328. And because I'm running this at 1 megahertz instead of 16 megahertz as the libraries would expect, I have to set the baud rate to 1/16 of what it's expecting. So it's at 9600 baud on the micro side, but the library will take that 9600 baud and expect a bus rate of 16 megahertz. So it's really running 1/16 the rate. So I've set the terminal to accept characters at 600 baud, and if I start this up, I can see the values coming in from that I'm sending over the serial connection. So if I come here and adjust this pot from one end to the other, I can see the value goes all the way down to 0 at one end of the pot and all the way up to 1023 at the other end of the pot. So that makes this a 10-bit A to D, so we can measure voltages over that whole range, and the pot would provide those. And I could probably dial in each one of those values if I turned it very, very carefully, but you get the idea. So we get a full range of analog values now from my potentiometer on that analog pin. So now I've got the Hall effect sensor and the green LED hooked up. The green LED is on the GPIO pin and the Hall effect sensor is plugged in to the analog pin. And I don't need an analog pin for the Hall effect sensor, but because the pin was convenient, I plugged it in there. I could use it in digital mode, but I've chosen to use it in analog mode to show actually you can actually do that if you really want to process a digital signal. You just have to set up thresholds. So my green LED is on, and if I move the magnet close to the Hall effect sensor, we can see the LED goes off. And if I bring it away from the Hall effect sensor, we can see that these rare earth magnets are quite powerful, and they set off the Hall effect sensor from quite a distance away. So there we go. There's the digital and analog section with the Hall effect sensor and the LED working.